Alright everybody, in this video we're going to look at a few examples related to the Squeeze Theorem, also known as the Sandwich Theorem, Homer Simpson's favorite theorem. The Squeeze Theorem is a reasonably straightforward proposition for us. What we have is we have three functions, and the one that we're interested in is the one in the middle, g of x. And so we've got three functions where one is always smaller than another, which is always smaller than another. And so, if we're trying to find the limit of this middle function, and we know that this first function is always smaller than this function, and this second function is always bigger than this function, and we know that those two functions share the same limit, that means that the middle function has to share the same limit. And that's the reason why this is called the Squeeze Theorem, or the Sandwich Theorem, is because the function that we're interested in is squeezed between the other two. And, you know, back when I was in school, it was more frequently referred to as the Sandwich Theorem, and the outer two functions are kind of your two pieces of bread, and then the good stuff in the middle is the function where you're trying to find the limit. I would recommend you read through the text here. It gives you a few little tips about how to determine what would be good functions to use for squeezing purposes. I'm going to kind of skip over that at this point in time and get down to the examples. Let's look at example 1. We're going to find the limit as x goes to 0 of x squared times cosine of 1 over x. Now, cosine of 1 over x is relatively complicated, and it's impossible for us to find this limit via substitution, because if we substitute 0 in for x here, we've got division by 0, and so we're taking the cosine of something that's undefined. So what we'll do instead is we'll look for kind of boundaries for the cosine of 1 over x. And if you think about it, you should know that both sine of anything and cosine of anything oscillate between -1 and 1, which means that we know that the cosine of 1 over x, no matter what it is in between -1 and 1. And since the cosine of x is in between -1 and 1, if I take this whole inequality here and multiply all the parts by x squared, I end up with this relationship right here. And I've got what I want to find the limit of in the middle. Now what's interesting here is we've set this up so that both of these other expressions in the inequality are things that we can easily find the limit of. We know that the limit as x goes to 0 of -x squared, we can find that by simple substitution. Substitute 0 in there, we get 0 as that limit. We know that the limit as x goes to 0 of x squared is the same deal. That limit's 0. So what we've got is we've got x squared cosine of 1 over x, which is sandwiched in between -x squared and x squared. And we know that the limit of both -x squared and x squared as x approaches 0 are 0. Therefore, by the Squeeze Theorem, we know that the limit as x goes to 0 of x squared cosine of 1 over x has to be 0. And frankly, you'll find a lot of times when we're doing Squeeze Theorem problems that the limit does end up actually being 0. That's a very common answer in Squeeze Theorem problems. Not always, but it's more common than any other solution when we're using the Squeeze Theorem. All right, continuing on, we're going to go to a few examples on the second page. Example 2, limit as x goes to 0 of x squared e to the sine of 1 over x. Again, we're going to use the fact that sign oscillates between -1 and 1, and that tells us that x squared times e to the -1 is less than or equal to x squared times e to the sine of 1 over x, which is less than or equal to x squared times e to the 1. And then, of course, the limit as x goes to 0 of x squared times e to the -1. Well, e to the -1 is just a constant, and so by substitution, this limit is 0. Same thing with x squared times e to the first. We've got 0 times e when we substitute that in, and 0 times e is 0, since e is just a constant. And therefore, by the Squeeze theorem, limit as x goes to 0 of x squared e to the sine of 1 over x, it's sandwiched in between those, and therefore it also has to be 0. All right, on to example 3. Suppose there are three functions such that f of x is less than or equal to g of x, which is less than or equal to h of x whenever x is near 2. If f of x is this polynomial and h of x is cosine of pi over 2 times x, then find the limit as x approaches 2 of g of x. So we're told in the lead into this problem that we've established this relationship already. We know that f of x is always less than or equal to g of x, which is always less than or equal to h of x. So even though we don't know what function g of x is, we do know that it's sandwiched in between f of x and h of x. And so if we take the limit as x approaches 2 of f of x, and the limit as x approaches 2 of h of x, and they're both the same, that means that since g of x is sandwiched in between them, the limit as x approaches 2 of g of x will also be that value. So we'll go ahead and evaluate these limits. We'll find the limit as x approaches 2 of f of x by just substituting 2 in everywhere for x. And calculating, that's -1/3 times 8, so -8/3 plus 4 minus 7/3. And if we calculate the value of all that, that ends up being -1. We'll do the same thing to find the limit as x approaches 2 of h of x. We'll substitute 2 in here for x. That's the cosine of pi over 2 times 2, or the cosine of pi, and the cosine of pi is -1. So we ended up with the same limit value, and therefore the limit as x approaches 2 of g of x is equal to -1. Now, what would have happened if we had found both of those limits and they would have had two different values? For instance, say the limit as x approached 2 of f of x was -1, but the limit as x approached 2 of h of x was 3. Then we can't really draw a conclusion as to the exact value of the limit as x approaches 2 of g of x, but we would know that it's between -1 and 3. I mean, that's not really helpful to say, hey, the limit of this function is somewhere in this range of values, but at least it allows us to narrow down a little bit our conception of where that limit is. All right. Last example of the lesson. Use the fact that sine of theta is less than or equal to theta, which is less than or equal to tangent of theta, to find limit as theta approaches 0 of sine of theta over theta. So this is a sandwich theorem problem, even though you don't immediately recognize it as such. We've got a relationship between three expressions here in this inequality, and what we want to do is we want to turn this middle portion through some algebraic manipulation into the expression sine of theta over theta. And if we can do that, then we'll be able to apply the sandwich theorem to find that limit, because we'll have that sandwiched in between two other expressions. Notice I interchangeably use the terminology squeeze theorem, sandwich theorem. They are the same theorem. Some places you'll see them referred to as one and some places as the other. So the first thing I'm going to do is I'm going to take all three parts of this inequality and I'm going to divide them by sine of theta. Because now I almost have what I want in the middle there. I have the reciprocal of it. If I simplify this a little bit, sine of theta over sine of theta is going to be 1. And tangent of theta over sine of theta, if you think about that, tangent of theta over sine of theta is equal to sine of theta over cosine of theta times 1 over sine of theta. The sine of thetas cancel out, and that's equal to 1 over cosine of theta. So I've manipulated into that relationship. Now I'm going to take the reciprocal, and that maintains the inequality that's present. So 1 is less than or equal to sine of theta over theta, which is less than or equal to cosine of theta. And so we have a relationship where sine of theta over theta is sandwiched in between these two other expressions. So in order to find the limit as theta approaches 0 of sine of theta over theta, we'll take the limit as theta approaches 0 of 1, and that's just 1. And we'll take the limit as theta approaches 0 of cosine of theta, and that is also 1. Can just substitute 0 in there for theta, and cosine approaches the value of 1. And so therefore, by the squeeze theorem, the limit as theta approaches 0 of sine of theta over theta is equal to 1. All right. That's it for today's video and the lesson on the squeeze theorem, aka the sandwich theorem. See you again next time.